Now we're going to talk about mass percent composition of compounds. We have the mass percent is the element's percentage of the total mass of the compound. So it's part per whole. So the mass percent composition of sodium in sodium chloride is 39%. So that's saying that for every 100 grams of sample of sodium chloride, we have 39 grams of sodium. And this is determined using experimental data. So to figure this out, the mass percent of element X, we take the mass of X in the sample of the compound of that element, and we divide it by the mass of the whole sample. So it's part per whole times 100 to turn it into a percentage. So if we have 0.358 gram sample of chromium react with oxygen, it gives us a chromium oxide or a metal oxide that has a mass of 0.523 grams in the lab. So what is the mass percent of chromium? Very simply, we have mass percent of chromium, remember, is the mass of X in the sample. That's our part. And this is 0.358 grams of chromium. Now, the whole here is the metal oxide. That's the compound that we formed. So it's got the chromium and the oxygen in it. So this is 0.523 grams. And then we multiply that whole thing by 100 to get a percentage. So 68.5% of chromium. That's our mass percent. So in this sample of metal oxide or chromium oxide, 68.5% of that is. Okay, now we can use the mass percent as a conversion factor to convert between grams of a constituent element and the grams of compound. So let's go to the FDA recommendation that adults consume less than 2.4 grams of sodium per day. So how many grams of sodium chloride can you consume and still be within FDA guidelines? And we know that NaCl is 39% sodium by mass. That's been experimentally figured out. So we want to start with our given of 2.4 grams of sodium. Well, and then now we want to use this as a conversion factor. Remember, 39% means per 100. So there's 39 grams of sodium per 100 grams of sodium chloride, right? That's what percent means. So we can use this as a conversion factor, just like we learned in chapter 2 and we've been doing. So there's 39 grams of sodium per 100 grams of sodium chloride. And so this gives us a shortcut way. If we know the experimental mass percent, it's a shortcut way of figuring out how much sodium we have in sodium chloride without doing the 4-step process that we did in the last section. So the grams cancel out for sodium, and we are left with sodium chloride. And so this amounts to 6.2 grams of sodium chloride. So we would have to consume no more than 6.2 grams of sodium chloride to maintain the FDA guide. Okay, now you go ahead and you give this a try. If a woman consumes 22 grams of sodium chloride, how much sodium does she consume in grams? Okay, so this is in grams. All right, so let's start with what we're given, 22 grams of sodium chloride this time, okay? And remember that we were given that sodium is 39% by mass, so there's 39 grams of sodium for every 100 grams of sodium chloride. And this time, since we have sodium chloride on the top, we're going to put grams of sodium chloride on the bottom. And we want to put our desired unit on the top here, our grams of sodium. And so we know there's 39 grams of sodium for every 100 grams of sodium chloride. the sodium chloride cancels out. We're left with grams of sodium. And so we end up with 8.6 grams of sodium. So she is consuming well above the FDA set limit. Now, what if we don't have experimental data that tells us the mass percent composition of an element in a compound? We can also calculate the mass percent of any element in a compound from the chemical formula of that compound. So if the chemical formula is known, then we can theoretically calculate the mass percent of any of its constituent elements. And we do that again based on this part per whole times 100. So we have the mass element X in 1 mole divided by the mass of 1 mole of compound times 100%. So let's do an example. We want to find the mass percent composition of chlorine in C2Cl4F2, which is known as Freon 114. And these are known as CFCs for chlorofluorocarbons. And you know them as Freon, which is a coolant or a refrigerant. And these have been found to be very detrimental to the depletion in the ozone layer. And so the damage is caused by the chlorine here. That is why we want to know how much chlorine is found in this Freon 12. So how much will that end up damaging the ozone layer? So let's go ahead and figure this out. So we have the mass percent of chlorine. And remember, we've learned that we have part per whole, right? So we have, in this here, we have 4 moles of chlorine for every 1 mole of Freon 114, right? So we just multiply 4 times the molar mass of chlorine divided by the molar mass of the entire molecule. And this is found to be 203.8 grams per mole. And of course, we multiply the whole thing by 100 to get a percentage. And when we do this, these just cancel out because we don't have units and it becomes unitless. And so we end up with 69.58% chlorine and Freon 114. And then this will help scientists know how much damage is being done in the ozone layer based on how much of this Freon 12 that we're putting out in the environment. Okay, go ahead and give this a try. Acetic acid, and I give you the formula for that, but you should know that from our nomenclature. It's the active ingredient in vinegar. So let's calculate the mass percent composition of oxygen in acetic acid. So we have the mass percent of oxygen this time. So we have 2 oxygens with 16.00 grams per mole, molar mass of each oxygen, now divided by the molar mass of the whole thing, which is acetic acid, and that is 60.05 grams per mole. And then we multiply this whole thing by 100 to get a percent. Of course, these units cancel out, and we end up with 53.29% oxygen in acetic acid.